Hey, this is Horner. We're going to look at 18.9 and 18.10. 18.9 is about measuring current and voltages. So we've done a lot of this in class, and we've used all kinds of different instruments. The instrument that we've used the most has been the multimeter, so it kind of looks like this. And it'll measure all kinds of different things, hence the name multimeter. So a multimeter is usually an ammeter or a voltmeter. Ours will do both. And remember, we've talked about having to switch the terminals to do this, and we've talked about the settings that it needs to be on. So whenever we measure voltage, we always use a voltmeter, and an ammeter just measures current. So that's really the basics behind this. Here we've got another one. This one talks about what a galvanometer is. So this is an analog voltmeter or an analog ammeter. And basically uses magnetic forces in order to make the needle move back and forth. It's got an internal resistor in it, and that's what gives you your values for the ammeter and the voltmeter, which is termed a galvanometer. So you'll see the old needle ones probably in the lab, but we probably won't use those. This one is example 1810, and it just says if the internal resistance of a galvanometer is 100 ohms and it deflects full scale for a current of 100 microamps, what is the resistance the shunt resistor would have to make for an ammeter measuring currents up to 10 amps? So to do this one, it's got a shunt resistor, or it's got a resistor that's just going across within the ammeter itself. And that resistor then helps make the value that you actually read for 10 amps come up to be 10 amps. If you tried to do this and you had that internal resistor there, it would not read correctly. So this resistor in parallel will help the galvanometer read the correct current as it goes through. So the solution here is we just took our voltage, which is our potential, which is current. So there's our current times our resistance. And here we end up with 0.9999 amps times the resistance of that shunt resistor. So now we just need to rearrange our equation, and we end up with about 1 milliohm. So in order to have accurate measurements, that ammeter needs to have a really small resistance. An ideal ammeter doesn't have any resistance at all. So just wanted to show you kind of some of the math that goes behind this. If I look at this is it's also possible, if I want to, I can construct a voltmeter by connecting a resistor in series with a galvanometer. So here I've got two resistors in series inside that galvanometer, and that allows us to go through and have a good voltmeter. So we don't really affect that circuit, we really want to make sure that the voltmeter has a pretty large resistance. So an ammeter needs to have low resistance, a voltmeter has to have high resistance. So an ideal voltmeter has an infinite resistance, so big that you won't get anything go through it at all. To measure the voltage in a circuit, we always want to put the voltmeter on either side of the object that we're trying to measure the voltage of, and you'll notice that the ammeter is in series. So ammeters are in series, voltmeters, these are in parallel. And if I want to measure the voltage that includes the ammeter, then I would have to make sure I put that voltmeter on the outside of that ammeter. So just a little bit of a difference between the two. For 1810, these are RC circuits, and RC stands for resistance and capacitor circuits. And these are often used to control timing. So if you think about your windshield wipers, they're on a delay, and what happens is there's a time delay between the resistance and the capacitance in the circuit. So we're waiting for that capacitor to charge. That's the delay that you see when the wipers come down and stop. And then once that capacitor is fully charged, it discharges, and your wipers go across, and it comes back, and you have to wait again. And you can actually change that. We also can use this RC circuit as just a really simple model of transmission of nerve impulses. So when nerves work, we see these things. This is a good example of an RC circuit. So you'll notice we do have a resistor and we have a capacitor. Initially we have an open switch here, and when the switch is closed, the current begins to flow and charge starts to build up on the capacitor. So at any instant, Kirchhoff's loop rule does require that our EMF here minus the voltage across the resistor minus voltage across the capacitor should equal 0. So for example, if I have a 12 volt battery here and this resistor takes 6 volts, then this capacitor can charge up to almost 6 volts, or it should charge up to 6 volts, because 12 minus the 6 does give you that 0. So that's the loop rule and how it applies to RC circuits. Just after I close that switch, the potential difference across the resistor is equal to the EMF since the capacitor is uncharged. So initially there's a really big current that flows, and then after that voltage drop across the capacitor increases, the voltage drop across the resistor decreases. So if this is a 12 volt battery, initially what happens is this starts at 12 volts and then goes down, as this one starts at 0 volts and moves its way up until it's fully charged. So that's essentially what this slide is trying to tell you. For the next part here, long after the switch is closed, the potential difference across the capacitor is nearly equal to the battery, and the current is very small within the inside. So if we want to use calculus, which we won't do, but we can look at this equation, and it just says that the voltage for a capacitor over the time it takes to charge. So this is in reference to, so this is not really part of the equation. So they'll say VC here, and they'll use the T in the parentheses, and this T you don't multiply times the VC. It just means that we're taking into consideration the amount of time it takes for it to charge without using the time here. Instead, the time to charge is actually way over here, and then we have another thing, looks like rho, looks like kind of a torque if you want to, and it's equal to the resistance times the capacitance, and we call that the time constant for the RC circuit. And that time constant would be based on the capacitor and the curve that you end up with. So just an important thing here. We can use the loop rule to find the current, and so here we're going to find out that the current is equal to the EMF over the resistance times e to the negative t over that time constant again. And so what's really cool is here we can derive what the time constant is, and it is just the resistance times the capacitance. In the next slide, oops, we're going to back up one here. In the next slide, this is power inside of an IC circuit. So for a charging capacitor, the power is the rate at which energy is stored in that capacitor. So while it's charging, that EMF does supply energy at a rate of just the current times the voltage. And it's equal to the sum of the rate of the resistor plus that for the capacitor. So you'd have to add the two together to see what the total power is, but you can find the power in each one at any particular time by finding out one and then just subtracting off the power total to find the other one. So energy here has to be conserved as it goes through. In this problem, I've got 2.5 microfarad capacitors. They're in series, and they're connected to a 50-volt battery through a 4 mega ohm resistor. And that resistor we're talking about at time 0, so before we put this down. They want us to find the charge in the capacitors at 1 second and then later at 3 seconds. Then for B, they want us to find the current in the circuit at the same 2 times. So we're going to, since we're looking at a time relation here, we're going to use the VC is equal to E times 1 minus e to the negative t, that's our time, divided by our RC constant here. And remember, this isn't really voltage. Well, it is voltage. It's potential difference, but it's for the battery itself. Okay, we can find the charge from Q is equal to V times C, or C times V. And the charge on the two capacitors is equal to the charge on the equivalent capacitor. So we're going to use our equation for current here to do that. To begin with, remember the capacitors in series. You have to add those up with the reciprocal function, or you have to do an inverse. So here we find out that it's about 0.250 microfarads. Our constant is just the resistance times the capacitance, that equivalent capacitance. So it's 4 times 10 to the 6th times 0.25 times 10 to the negative 6 farads, and we get 1 second. And so QF here, that's Q is equal to CV, so we're finding the charge. The charge is going to be 12 microcoulombs. And so if I want to find QT, you can set up this equation. So here's QF, and then that helps us solve for the overall charge itself. So at 1 second, this t over our time constant should be 1. So we're going to plug that into the previous equation that we just derived. We've got 12.5 microcoulombs is our QF, and we're going to multiply that times 1 minus, and then it's E on your calculator. It's the lowercase e to the negative 1 power. When you do that math, you get about 7.9 microcoulombs. And if we do it at 3 seconds, we see that t divided by our RC constant should be equal to 3. And so when we plug that in, we get 11.9 microcoulombs. So this should be bigger than this one because it should store more charge at that time. For letter B, they want us to find the current, and so here the current is equal to the change in voltage, the EMF of the battery divided by the resistance, so it's 50 over 4 times 10 to the 6th ohms, because it's mega ohms, and that's 12.5 microamps. So now we can use our equation I is equal to our original current, and that's what we just found, times e to the negative t over our RC constant again here. But remember, this just represents the amount of time that's passed. So now we can plug in our time, plug in our current, our original current, and we end up with 4.6 microamps. After 3 seconds, when this is going through, we end up with 0.622 microamps. So those are the solutions to the two. Also in RC circuits, the capacitor is first charged by voltage when I take the switch and I close it. And then you'll notice here that if I close this switch and leave this one open, everything will flow through the capacitor charge. And then when I open switch number 1 and close switch 2, now I'm going to get a flow of charge going this direction. So now the capacitor acts like a battery in the sense that it applies some energy to the circuit, but it's not a constant potential difference. So the voltage here is going to decrease as time goes on. That's a capacitor. And for a EMF source like a battery, it stays pretty constant. The loop rule requires that the voltages across the capacitor and the resistor be equal as we look at it. So as the capacitor discharges, the voltage across it decreases, and decreasing voltage across the resistor means that the current has to be decreasing. So the current here we know is a function of time, and we know that T is equal to RC, so that voltage across the capacitor that we have here begins at a maximum value and then decreases pretty quickly. So we say that it decreases exponentially. And you can see that in the curve here. So your voltage will go down exponentially as that capacitor is being discharged. And you can look at the time constants and how they change as they go through. The current is a function, really, of just that, of time is the same as in the charging circuit. So when it discharges, it has the same equation as when it charges. And then power for a discharging capacitor, the energy stored in that capacitor at a rate of, so here we've got current times voltage, and energy is dissipated, in that, let's back up, at an equal rate. So that's essentially what's happening as it's discharging. So we've got that current in the resistor times the voltage of the resistance is equal to current times the voltage in the capacitor. So those go through at an equal rate. So they basically get rid of energy at the same rate. This is about electrical safety. So if you've ever been on a farm, one of the things that they do is they have a source of electricity. This is an EMF source, and we pass a current through a wire, and then if a cow or some other object touches that wire, then the current is transferred through the cow gets a shock, backs up away from the wire, and then that current, that loop is actually made by having a grounding rod down into the ground. So that's what you'll see here. If we did the same thing with people, and let's say that we have a refrigerator here, and you end up touching the refrigerator and it's plugged in, you could complete the circuit all the way through. So these old style plugs you don't see anymore. If that did short circuit, you get electrocuted by your refrigerator, and that would not be good. So what we do now is we have a 3-prong cord so that you no longer will get electrocuted by having a ground source over here like we did in the previous here. So here we've got a ground that's attached to one of the prongs. In this one, in the next one, we don't. We actually have a ground that's attached to one of the prongs so that the circuit, if it would short circuit, okay, to the case, the current would travel along the case and then through the 3-prong plug into the ground. So these things really will save your life. Those 3-prong plugs. You never want to break this 3rd prong off. So if you go into a house with just 2 and you break that off, that's not good. You can become electrocuted. And that is the end of those sections.